In this particular video, we will study about one of the most important and the simplest instrument, or let's say an optical instrument in hand, that is lens. It uses a principle of refraction across two spherical surfaces, that is spherical surface on one end where it enters from a particular medium to the glass, and the refraction through the other surface where it exits from glass to the other medium. So we will describe everything about lens, that is starting from lens maker formula to the lens formula itself, and also describing its applications. So let's see what do we have when we study lens. Now we shift our attention to lens. Lens being a very important instrument or tool, so as to put it, as far as the refraction is concerned. Every sort of refraction which we use in our day-to-day life, let's say eye or the lenses exactly which you know of, undergoes refraction through spherical surfaces. So for as far as the aspect of refraction from spherical surfaces are concerned, lens is the tool to study about. So let's start off with lens. So in these topics associated with lens, what we will do is we'll come up with a similar context, that is of that of mirror over here. Mirror being a very important or the most important aspect of reflection, use of reflection. So we came across mirror formula. In this aspect as well, lens is very important as far as refraction is concerned. So we will come across lens formula. So let's get going, or how we will come up with lens formula. Okay, so let's start off. So this is a lens, NL being the two top points of lens, mu1, mu2, mu1. I need two surfaces because lens will have one refractive index, and the surfaces across which it's going to refract and throughout the light has to have the same refractive index. That is as far as simplest case is considered. So we are right now studying the simplest case, that is I have mu1 across lens of refractive index mu2. Principal axis, P1, P2 being the poles of the two surfaces, C the center of the lens, C1, C2 being the radius or the center of curvature for the two surfaces over here. So C1 will correspond to the center of curvature of this sphere, C2 will correspond to this. Sorry, it's the other way around, that is C1 will correspond to this and C2 will correspond to this. Now the incident ray from a particular object goes like this. I end up getting image at I1. So this is in general. So from this, from all the notation A, C2, P1, C, P2, C1, I1, N1, N2, we will have to come across a lens formula that relates object distance, image distance and the refractive index. R1 and R2 being the radius of curvature. So obviously I am looking out for something which relates U, V, R1, R2. So I have U, V, R1, R2, and I also have mu1, mu2. I want something which relates all of them together. So that's where lens maker formula kicks in. So if you give me a particular setup, that is I have concavo convex, convexo concave, plano concave, plane refracting surfaces, any type of refracting surface you throw at me, that is a combination of two refracting surface, one which is facing an incident light, the other one which is throwing out the refracted light. So I need two surfaces, two refracting surfaces. If you give me those two refracting surfaces, their refractive indices and the refractive index of this surrounding, I'll come up with a formula which effectively tells me how good the lens is. That is given by lens maker formula. So I will exactly find out what lens maker formula is by simply applying refraction through spherical surfaces. Now please keep this point in the mind. It has been specifically given at the starting in the brackets. I will tell you the importance of it, but first keep this in mind. As if the object is in the denser medium and the image is formed in the rarer medium. If you just get hold of this line, it simply gives me that although the object is not in the denser medium,
it seems like it is, and the image is formed in the rarer medium, right? So corresponding to that thought or that understanding of this particular statement in the background, let's study what this surface has to say. LP1N given over there, LP1N, when the incident light just hits the surface, right? So at that surface I'm talking about LP1N. So applying that, the refraction through the spherical surface, we end up getting mu1 by Cu plus mu2 by C1 equals to mu2 minus mu1 by CC1, as the image is formed in the denser medium. Okay, it doesn't actually forms in denser medium, right? It appears that it is forming in denser medium, right? So the image which is formed because of the first surface will now act as the object for the second surface, right? For the refraction at LP2, now this image will act as an object, right? This image will now act as an object for this surface. So that's why, as if the object is in the denser medium. So that's the context which I was talking about in the initial sentence. So this expression and this expression, using these two, I will get hold of what is a lens maker formula, or what that whole setup, including the surrounding and including the thing which we have, that is the lens, we have to come across the effective focal length, as if a particular lens of this much focal length was placed in front of an object. That's lens maker formula. So substituting the values with the sign convention, we will get hold of lens maker formula. This is lens maker formula in a very crude sense. Now we will substitute the values of what is CO, CI, CC1, CC2 in terms of, mind it, in terms of U, V, R1 and R2. Right? So I have to express this in terms of these quantities right now, U, V, R1 and R2. And this is what we are going to do. That is 1 by minus U plus 1 by V equals to mu2 minus mu1 by mu1 multiplied by 1 by R1 minus 1 by R2. This is lens maker formula, and I know that since mu2 by mu1 equals to mu, and substituting the value over here for this particular expression, I will end up getting this. That is just to find out the relative refractive index so as to make the expression look, pleasant or tidy. So that's what I'm doing over here, tidying up the expression, nothing special about it. Now, further down the lens maker formula, when the object is kept at infinity, the image is formed at the principal focus. So U is equal to minus infinity, V is equal to plus F. So effectively, I have found out a very, that is, irrespective of how much complex the setup looks like, I am right now able to find out, using the parameters of the setup, to find its effective focal length. And this, my friend, is the lens maker formula. Right, as written over here, it's a lens maker formula, and this is how we have used it. That is 1 by V minus 1 by U equals to 1 by F. So if a particular setup is given, refractive indices of the surfaces are given, that is lens and the surrounding, everything is given, radius of curvature of both the surfaces are given, and you have been asked to find out where the image will be. So first we will compute what is the focal length concerning the surrounding and the thing which has been given to me, whether it is a lens of water or a glass or a diamond, whatever. I need to find out the effective focal length first, then given the object distance and using the lens maker formula, I will get hold of the image distance. So finally, my main agenda is to find out where the image will be. So I have the object distance because that's my choice, my call, and regarding the different parameters over here, I can find out the effective focal length. So this aspect will be done, this aspect will be done, so we can easily procure the object of our interest, image distance. So parameters of the lens, just brushing up of the concepts of what these terminology stands for. First principle of focus. First principal focus is the point on the principal axis of the lens at which if an object is placed, the image would be formed at infinity. So this is how the first principal focus is defined. That is, place the object on the principal axis, right, and the image will be formed at infinity. That point is called as principal focus. It looks like this. F1 is that point, let's say the principal focus, the image is formed at infinity. This is for convex lens, so keep that in mind. So for concave lens, it will be kind of virtual in nature. So we'll do that as well. Now for the concave lens. For the concave lens, obviously, that point will come out to be virtual, because I cannot keep a particular object at this particular point and at this particular point at the same time, right? So that point actually comes out to be F1. That is, if I keep the object at this particular point F1, the image seems to be formed at infinity. Mind it, it's not a real point. Now second principal focus. Second principal focus is that is the point at which the principal axis of the lens, at which the image is formed when the object is kept at infinity. So the second principal focus is when the object is at infinity and the image is formed at that particular point, which is this. F2 is that particular point. F2 is that point of interest. My object is at infinity, the image is formed at that particular point. So that is my second principal focus. Again, for concave it will be different. Again, an imaginary point, object placed at infinity, the image is formed at that particular point. And F2 is the second principal focus for concave lens. Now for concave lens, so the Gaussian forms of lens equation. So the Gaussian form is basically to deal with the waves, that is the region which they have occupied, or the region around which I can see the object, I cannot see the object, the region in which I can see the image, I cannot see the image. These are denoted by these regions, right? So make sure that you are very thorough with the triangle. That is, I will be comparing the triangle ABC, which is given in the purple, if you can, pink, sorry, if you can see it. Then the triangle A-B-C, again a bit of purple and a bit of green. So I will be comparing these triangles and hope to find out the relation between the object distance, image distance and the radius of curvature. So please keep this in mind right now. From the next slide onwards, we will be deriving up the thin lens formula. So this purple pink triangle, green triangle, combination of green and purple pink triangle, keep that in mind. And what are these entities? That is, this is the focal length that's given, this is the radius of curvature, object distance, image distance and everything. This is the image height, this is the object height. So as A dash B dash, now using the properties of similar triangles, we'll end up getting these ratios quite easily. So A dash B dash is equal to divided by B equals to CB dash divided by CB. Again, new set of triangles, we'll end up getting A dash B dash divided by MC is equal to B dash F2 divided by CF2. Again, you shouldn't be worried about this. That is, I'm just dictating out the terms right now because it's easy. So even though if you feel low on working these things out, you can quickly refer back to the setup, pause it and run these through. Believe me, they are very simple. So again, use of similar triangles, which you have done thoroughly in your class 9 and I guess in class 8 as well. So again, new set of similar triangles, we end up getting this relation from that, and respecting this sign convention which we already have and substituting the values of the different distances, the horizontal distances. So all the horizontal distances will be expressed in terms of, as I've said, U, V and F. They will be expressed in these terms whatsoever, either addition or subtraction or combination of these three. So we end up getting the most coveted thin lens formula. So it's 1 by V minus 1 by U equals to 1 by F. V being the image distance, U being the object distance and F being the focal length. Now, the magnification and the power, linear magnification is basically the ratio of the object height the ratio of the image height divided by the object height. So it's m is equal to I by O, or corresponding to the initial diagram, that is the Gaussian diagram which I showed you earlier, the ratio will come out to be this. Respecting the sign convention, we end up getting magnification to be this. M is equal to I by O, that's completely standard, equals to V by U. So V is image distance, again U is object distance. So make sure this is a very important property and it's being used extensively. So please make sure you keep this in loop whenever you study about refraction. Now magnification, obviously I can play along that now that I have lens formula. So in the magnification expression of m is equal to my V by U, I will definitely now play along, substitute let's say U in terms of V and F, or V in terms of U and F. So I end up getting these two other alternate expressions for that. Power of lens is basically the ability to bend a ray of light falling on it. So the amount to which I can bend the light falling on me depends upon my focal length. Instead, it actually depends upon the reciprocal of the focal length. So it's given by diopter.
Now this is a simulation which we can work around with refraction of light to a lens. So if you look over the portal, I have no rays, that is without showing any rays. Let me find out where the image is. Now that will be pretty hard for me. I have marginal rays, that is just play along with the basic set of rays which sounds decent enough for me, that is 2 or 3 light rays will do. Principal rays, again the light ray passing through my principal axis. So if you can look at this, these are my principal rays and my object is over here. Now obviously if I place my object over here, I will end up getting my image somewhere here. And so let's for a while put the object over here. Then many rays, obviously I want multiple set of rays, so as to just fancy myself how the object will look. Okay. So this is one. Then I can change the radius of the curvature of the lens, that is if you see the effects. So this what happens when I change the let's say the radius of curvature of my lens. See, increasing the radius of curvature, the light rays start to converge at a very far off point. So let me put up with a decent amount of radius of curvature. This sounds good enough. Now refractive index, what will happen if I play along with the refractive index? So if I play along with the refractive index, you see this is what happens. Decreasing the refractive index, right, I'm not able to bend light more. So if I increase the refractive index, I'm able to bend light more, so they try to converge at a closer point. And so let's again put up back where we found it. Okay, the diameter, obviously if I play along with the size, let's say it's 0.03, that's what I can go to. And if I increase my size to, let's say, greater heights, so I will be able to converge more amount of light rays. So this is very helpful for you to understand how the images are formed when I'm keeping my object over here, basically let's say over here or over here or anywhere. Let's say I put up on my focus, right? So let's say this on this point, X points, these points X, they are actually marked to denote that beyond that point you are sure to get up the virtual image. So this is what will happen if I see this point. The moment I reached X, see what happens actually. A light ray will kind of shoots up, right, and suddenly changes its behavior. It's just about, or it's just kissing the top edge right now. So the moment I get it beyond, now it's totally off. So this is how we'll end up getting the virtual image, right? See this. This is where I end up getting my virtual image between the focus and the pole. Again, the other way around, I can move it like this. Right, so this is basically convex lens. I can play along with convex lens. So this is an interactive simulation which is an in-house production, so you can enjoy it whenever you want. So let's get on with the lecture.
Now we'll work out a particular problem based on this. Let's say I have a lens over here whose focal length is 10 centimeter, and there's an object placed at 20 centimeter from the lens, and there's another lens which is placed at 40 centimeter from me. So when the object is placed at 30 centimeter, what I observe is I end up getting a highly magnified image. So I will write it down what I observe. That is the highly magnified image, the most enlarged version of the object. I need to find out what is the focal length for this. Now, I clearly know that if it's 20 centimeter and this is 10 centimeter, the image will be formed at 20 centimeter from this particular point. So if an image of this particular point is formed at 20 centimeter from this end, why? Because this is the radius of curvature. So if the object is placed at the radius of curvature, I'll end up getting an image at the radius of curvature on the other side. From this point, I'm getting a highly magnified image. It means this point lies on the focal length, right? So it's 1 by v minus 1 by u equals to 1 by f. So my object distance is basically 20 centimeter. So my object distance is 1 by 20. I've substituted with respect to sign as well. And v is infinity and f is 1 by f. So my focal length comes out to be 20 centimeter. So the focal length of this particular lens is 20 centimeter in order to satisfy this, that is getting a highly magnified image.
Now that we have studied lens maker formula and the lens formula, we clearly know about everything about refraction. So why an importance about lens is given? Because our eye itself is a convex lens. So that's why we have studied extensively about lens, and we have to figure out everything about lens because that's how we can rectify our defects in our eye. So that's the reason why we actually studied so much about lens.